So let's finish up on chapter 4. There's 4 properties that make metals different from all the other things on the periodic table. Electrical conductivity, which is the ability for metals to transmit electricity. They do this because metallic bonds are formed in such a way that the electrons can move freely among the mass of atoms. The next is thermal conductivity, which is always related to electrical conductivity. If something is electrically conductive, it's also thermally conductive. It's just the ability for a material to move heat. So something like aluminum has very high electrical conductivity, whereas something like stainless steel has lower electrical conductivity, thermal conductivity. Formability is the ability for a material to be deformed and not fracture. So you can deform a rock, but it's just going to shatter into bajillion pieces. Metals can be ductile or malleable or both. Malleability is the ability for a metal to be rolled. Ductility is the ability for a metal to be pulled apart. Most metals that are malleable are ductile, but not all. So for example, lead is very malleable, but not ductile. It cannot be drawn into wire. The last property is reflectivity. Metals, for the most part, reflect 100% of light. The reason something like aluminum might look dull is because the outside skin is aluminum oxide. It's been joined with oxygen and it forms a layer that is not particularly reflective of light. Aluminum oxide isn't really a metal, it's not conductive. Titanium does a similar thing, and even the rust on iron and steel is iron oxide. So the oxygen joins with the iron and makes a new compound that's not quite a metal. So let's talk about the crystal structures in metals. So there's a lot of terms that are going to be thrown around. There's a few we're going to talk about. Unit cells, crystal structures, and space lattices are the first. So the unit cell is the arrangement of atoms, the smallest arrangement of atoms that will fit into a space lattice together. So every unit cell is a little bit different depending on what metal and what phase it is. Most metals have one kind of unit cell. So we'll talk about the 3 we're going to talk about today. Trust me, there's many, many more. Body-centered cubic, face-centered cubic, and hexagonal close packed. It's just how the atoms are arranged. Now, these unit cells are going to join together in orderly structures. These orderly structures are known as the space lattice. So there's a whole bunch of unit cells, and they're going to arrange themselves together, just like building blocks. So we can't really see the unit cell or the space lattice under the microscope. But when the space lattice gets big enough, so thousands, millions of unit cells all lined up, they'll form crystals. So how do we tell the crystals apart, right? Wouldn't all of the metal just be one big space lattice, right? What happens is that as they get bigger, they start to fracture. So you end up with space lattices that are pointed in different directions. So these crystals are known as grains. There's a clear separation between these crystals, and this separation is called the grain boundary. Now this can be seen under a microscope. It's just where the different crystals meet together, but they look like, if you've ever seen galvanized steel, there's big, kind of like icebergs in an ocean. They're packed close together, but they're all jagged, maybe like a puzzle. So these grains are very, very important for what we'll study in this course. The size of the grains and the way they're arranged will affect the macroscopic properties that we're really interested in. So strength, ductility, corrosion resistance, a whole bunch of things are affected by these little tiny grains. So the 3 unit cells we're going to cover are body-centered cubic, face-centered cubic, and hexagonal close packed. But the body-centered cubic has a cube shape. There's an atom at each of the corners and one in the middle. So iron at room temperature, vanadium, tantalum, molybdenum, tungsten, all form body-centered cubic structures. They're somewhat formable. Face-centered cubic structures have atoms at each of the corners of the cube and an atom in the middle of each face. So this is the structure that iron at elevated temperatures is going to take. Aluminum, copper, platinum, and gold all have this structure. This is typically the most malleable of the structures. Hexagonal close packed is a hexagon shape, and I won't be able to describe where the atoms are for you, but there's a lot of faces. What this essentially does is make the unit cells more difficult to slide past each other. These materials are typically less formable than the others, so things like magnesium, titanium, and zirconium have this particular structure. When atoms slide by each other, millions at a time, deformation occurs whenever the metal is going to change, usually as a result of some kind of force. Now we can't see the individual atoms slide by each other, but we can see the results in the crystal structure and the arrangement of the grains. We can really tell this by the grain boundaries. These can be etched with an acid and seen under a microscope. Where the actual grains slide by each other are known as slip planes. So we can study these slip planes and see kind of what's going on with the material, what kind of stress it may have been under, and what kind of properties may result. So let's talk about 3 terms we'll be using: mixture, solution, and phase. They're all similar, but they mean different things. A mixture is a combination of 2 or more substances that remain unchanged individually and can be separated. So a mixture would be a cereal and a bowl of milk. They're 2 totally separate things that can be separated. This can happen with metals. So there's certain alloys that you can see under the microscope never totally join with the parent metal. The next is a solution, which is a combination of 2 or more substances in which one substance is completely dissolved in another. So this would be like sugar in hot water. Once the sugar gets in there, you can't get it out. So same thing with salt and water. You can't separate them out easily. I know there's certain ways you can do it, but for our purposes, they're inseparable. So this happens a lot when you add an alloy to a specific material. It literally disappears under the microscope. You can't see individual carbon atoms in steel, but you can see the new structures that those 2 elements create. A phase is any region of the material with measured properties that are constant or changing slowly and have one particular crystal structure. So this is big when we're studying iron and steel. Iron and steel have different phases at different temperatures, even though they're still solid. So you've probably heard of phases in water. So you have liquid, gas, solid. Steel has all those things too. Steel can be liquid, it can be solid. If you get it hot enough, it can even become a gas, right? It'll vaporize. But it has a lot of individual little phases in there. The metal, the crystal structures are literally gonna move themselves around when it gets heated up. These are known as phases. So in order to heat treat a steel, it's gotta be in a certain phase and then quickly cool down to another phase to lock it in, to lock in that extra strength and hardness. So we got a whole chapter on it. We don't have to go too much into it now, but phases are very important in our future studies.